address space. These include the counter/timer channel, CTC, the SIO, serial input/output, the DMA, direct memory access, the PIO, parallel input/output, and the DAT, dual asynchronous receiver transmitter. As the product line developed, low power, high speed and CMOS versions of these chips were introduced. 1. PIO Z84C 2008. 2. CTC Z84C 3008. 3. SIO Z84C 4008. Like the 8080, 8085 and 8086 processors, but unlike processors such as the Motorola 6800 and Mohs Technology 6502, the Z80 and 8080 has a separate control line and address space for I/O instructions. While some Z80-based computers such as the Osborne 1 used Motorola-style memory-mapped input/output devices, usually the I/O space was used to address one of the many Zilog peripheral chips compatible with the Z80. During the timing for an I/O read or an I/O write operation, a single wait cycle is automatically inserted by the Z80. Zilog I/O chips supported the Z80's new Mode 2 interrupts, which simplified interrupt handling for large numbers of peripherals. The Z80 was officially described as supporting 16-bit, 64 kilobytes, memory addressing, and 8-bit, 256 ports, I/O addressing. All I/O instructions actually assert the entire 16-bit address bus. Out, C, reg and in reg, C, places the contents of the entire 16-bit BC register on the address bus. Out, N, A and in O, N, places the contents of the A register on B8, B15 of the address bus and N on B0, B7 of the address bus. A designer could choose to decode the entire 16-bit address bus on I/O operations in order to take advantage of this feature, or use the high half of the address bus to select sub-features of the I/O device. This feature has also been used to minimize decoding hardware requirements, such as in the Amstrad CPC/PCW and ZX81. Second sources and derivatives, edit. Second sources, edit. Mostek, which produced the first Z80 for Zilog, offered it as second source as MK3880. SGS Thomson, now ST Microelectronics, was a second source, too, with their Z8400. Sharp and NEC developed second sources for the Mohs Z80, the LH0080 and PD780C, respectively. The LH0080 was used in various home computers and personal computers made by Sharp and other Japanese manufacturers, including Sony MSX computers, and a number of computers in the Sharp MZ series. Sharp developed the LH0080 and LH0080B to operate at frequencies of 4 MHz and 6 MHz, respectively. Sharp also developed LH0083 compatible with Z80 DMA. Toshiba made a CMOS version, the TMP Z84C00, which is believed, but not verified, to be the same design also used by Zilog for its own CMOS Z84C00. There were also Z8400, Z80 chips made by Gold Star, now LG, and the BU18400 series of Z80 clones, including DMA, PIO, CTC, DAT and SIO, in Mohs and CMOS made by ROM Electronics. The LH5080, LH5081, and LH5082, which are CMOS versions of the Z80, PIO, and CTC respectively, are manufactured by Sharp. In East Germany, an unlicensed clone of the Z80, known as the U880, was manufactured. It was used extensively in Robotrons and VEB microelectronic Mulhausen's computer systems, such as the KC85 series, and also in many self-made computer systems. In Romania another unlicensed clone could be found, named MMN80 CPU and produced by Microelectronica, used in home computers like TIM-S, HC, Cobra. Also, several clones of Z80 were created in the Soviet Union, notable ones being the T-34BM1, also called 18581, paralleling the Soviet 8080 clone KR580VM80. The first marking was used in pre-production series, while the second had to be used for a larger production. Though, due to the collapse of Soviet microelectronics in the late 1980s, there are many more T-34BM1s than 18581s. 1. Most Z80, MK3880. 2. NEC-PD780C. 3. Sharp LH0080. 4. Toshiba Z84C00. 5. East Germany RFTU880D. 6. Soviet T-34BM1 Z80 clone. Derivatives, edit. Compatible with the original Z80. 1. Hitachi developed the HD64180, a micro-coded and partially dynamic Z80 in CMOS, with on-chip peripherals and a simple MMU, giving a 1 MB address space. It was later second-sourced by Zilog, initially as the Z64180, and then in the form of the slightly modified Zilog Z180, which has bus protocol and timings better adapted to Z80 peripheral chips. Z180 has been maintained and further developed under Zilog's name, the newest versions being based on the fully static S180/L180 core with very low power draw and EMI noise. 2. Toshiba developed the 84-pin Z84013/Z84C13 and the 100-pin Z84015/Z84C15 series of intelligent peripheral controllers, basically ordinary MOS and CMOS Z80 cores with Z80 peripherals, watchdog timer, power on reset, and wait state generator on the same chip. Manufactured by Sharp as well as Toshiba. These products are today second-sourced by Zilog. 3. The 32-bit Z80 compatible Zilog Z380, introduced 1994, is used in telecom equipment. 4. Zilog's fully pipelined Z80 compatible EZ80 with an 8/16/24-bit word length and a linear 16 MB address space was introduced in 2001. It exists in versions with on-chip SRAM or flash memory, as well as with integrated peripherals. One variant has an on-chip media access controller, MAC, and available software include a TCP/IP stack. In contrast with the Z800 and Z280, there are only a few added instructions, primarily load effective address, LE, push effective address, P, and variable address 16/24-bit loads, but instructions are instead executed between 2 and 11 times as clock cycle efficiently as on the original Z80, with a mean value around 3 to 5 times. It is currently specified for clock frequencies up to 50 MHz. 5. Kawasaki developed the binary-compatible KL5C8400, which is approximately 1.2-1.3 times as clock cycle efficient as the original Z80 and can be clocked at up to 33 MHz. Kawasaki also produces the KL5C80A1X family, which has peripherals as well as a small RAM on chip, It is approximately as clock cycle efficient as the Z80 and can be clocked at up to 10 MHz, 2006. 6. The NEC PD9002 was a hybrid CPU compatible with both Z80 and X86 families. 7. The Chinese Action Semiconductors audio processor family of chips, ATJ2085 and others, contains a Z80 compatible MCUs together with a 24-bit dedicated DSP processor. These chips are used in many MP3 and media player products. 8. The T80, VHDL, and TV80, Verilog, synthesizable soft cores are available from opencores.org. 9. The National Semiconductor NSC800 announced in 1980 is used in many telesecurity Timon, TST, electronic cipher machines and the Canon X07. The NSC800 is fully compatible with the Z80 instruction set. The NSC800 uses a multiplexed bus like the 8085 but has a different pinout than the Z80. Non-compatible. 1. The Toshiba TLCS900 series of high-volume, mostly one-time programmable microcontrollers are based on the Z80. They share the same basic BC-HL9IY register structure, and largely the same instructions, but are not binary compatible, while the previous TLCS90 is Z80 compatible. 2. The NEC 78K series microcontrollers are based on the Z80. They share the same basic BC-HL register structure, and has similar, but differently named instructions, not binary compatible. Partly compatible. 1. Rabbit Semiconductors Rabbit 2000/3000/4000 microprocessors/microcontrollers are based on the HD6418/Z180 architecture, although they are not fully binary compatible. No longer produced. 1. The ASCII Corporation R800 was a fast 16-bit processor used in MSX Turbo computers. It was software, but not hardware compatible with the Z80. Signal timing, pinout and function of pins differ from the Z80. 2. Zilog's MOS Z800 and CMOS Z280 were 16-bit Z80 implementations. Before the HD64180/Z180, with a 16 MB paged MMU address space, they added many orthogonalizations and addressing modes to the Z80 instruction set. Mini computer features, such as user and system modes, multiprocessor support, on-chip MMU, on-chip instruction and data cache, and so on, were seen rather as more complexity than as functionality and support for the, usually electronics-oriented, embedded systems designer. It also made it very hard to predict instruction execution times. 3. Certain arcade games, such as Pang/Buster Brothers, use an encrypted Kabuki Z80 CPU manufactured by VLSI Technology, where the decryption keys are stored in its internal battery-backed memory, to avoid piracy and illegal bootleg games. 1. ASCII R800. 2. Hitachi HD64180. 3. Zilog Z180. 4. Zilog Z280. 5. Toshiba TMP Z84C015. Notable uses, edit. Desktop computers, edit. See also, list of home computers. During the late 1970s and early 1980s, the Z80 was used in a great number of fairly anonymous business-oriented machines with the CP/M operating system, a combination that dominated the market at the time. 4 well-known examples of Z80 business computers running CP/M are the Heathkit H89, the portable Osborne 1, the K-Pro series, and the Epson QX10. Less well known was the expensive high-end Otrina Attach. Some systems used multitasking operating system software, like MP/M or Morrow's Micronix, to share the one processor between several concurrent users. Multiple home computers were introduced that used the Z80 as the main processor or as a plug-in option to allow access to software written for the Z80. Notable are the TRS-80 series, including the original model, later retronamed Model I, Model 2, Model 3, and Model 4, which were equipped with a Z80 as their main processor, and some, but not all, other TRS-80 models which used the Z80 as either the main or a secondary processor. Other notable machines were the December Rainbow 100 and the Sequoia Chameleon, both of which featured both an Intel 8088 and a Z80 CPU, to support either 8-bit CP/M80 applications running on the Z80, or a custom MS-DOS that was not fully compatible with PC-DOS applications running on the 8088. In 1981, Multitech, later to become Acer, introduced the Microprocessor I, a simple and inexpensive training system for the Z80 microprocessor. Currently, it is still manufactured and sold by Flight Electronics International Limited in Southampton, England. In 1984, Toshiba introduced the Toshiba MSX-HX10 in Japan and Australia. In 1985, Sharp introduced the Hotbit and Gradient introduced the Expert, which became the dominant 8-bit home computers in Brazil until the late 1980s. Portable and handheld computers, edit. Use of the Z80 in lighter, battery-operated devices became more widespread with the availability of CMOS versions of the processor. It also inspired the development of other CMOS-based processors, such as the LH5801 from Sharp. The Sharp PC1500, a basic programmable pocket computer, was released in 1981, followed by the improved Sharp PC1600 in 1986 and the Sharp PCE220 in 1991. Later models of the Sharp Wizard series of personal organizers also were Z80 based. Laptops which could run the CP/M operating system just like the desktop machines followed with Epson PX8 Geneva in 1984, and in 1985 the Epson PX4 and Bondworld 2. While the laptop market in subsequent years moved to more powerful Intel 8086 processors and the MS-DOS operating system, lightweight Z80-based systems with a longer battery life were still being introduced, such as the Cambridge Z88 in 1988 and the Amstrad NC100 in 1992. The Z80-derived Z8S180 also found its way into an early pen-operated personal digital assistant, the Amstrad PenPad PDA600 in 1993. Hong Kong-based VTech produced a line of small laptop computers called Lasers based on a Z80. The last two were the Laser PC5 and PC6. The Sidco mail station Mivo 100, first released in 1999, was a standalone portable email device, with a Z80-based microcontroller. Texas Instruments produced a line of pocket organizers, ending in 2000, using Toshiba processors built around a Z80 core. The first of these was the TPS 6200, and after a lengthy production run of some dozen models culminated in their PocketMate series. Embedded Systems and Consumer Electronics, edit. The Zilog Z80 has long been a popular microprocessor in embedded systems and microcontroller cores, where it remains in widespread use today. Applications of the Z80 include uses in consumer electronics, industrial products, and electronic musical instruments. For example, Z80 was used in the groundbreaking music synthesizer Prophet 5, as well as in the first MIDI synthesizer Prophet 600. Casio used the Z80 in its PV1000 video game console. A good number of early 1980s arcade video games, including the arcade game Pac-Man, contain Z80 CPUs. The Z80 was used in Sega's Master System and Game Gear consoles. The Sega Genesis contains a Z80, with its own 8 kilobytes of RAM, which runs in parallel with the MC68000 main CPU, has direct access to the system's sound chips and I/O controller ports, and has a switched data path to the main memory bus of the 68000. Providing access to the 64 kilobytes main RAM, the software cartridge, and the whole video chip, in addition to providing backward compatibility with Master System games. The Z80 is often used to control and play back audio in Genesis software. Z80 CPUs were also used in the trailblazing and popular T8X series of graphing calculators from Texas Instruments, beginning in 1990 with the T81, which features a Z80 clocked at 2 MHz. Most high-line calculators in the series, starting with the T82 and T85, clock their Z80 CPUs at 6 MHz or higher. A few models with T8X names use other CPUs, such as the M68000, but the vast majority are Z80 based. On those, it is possible to run assembled or compiled user programs in the form of Z80 machine language code. The T84 Plus series, introduced in 2004, is still in production as of 2023. The T84 Plus CE series, introduced in 2015, uses the Z80-derived Zilog Z80 processor and is also still in production as of 2024. In the late 1980s, a series of Soviet landline phones called AON featured the Z80. These phones expanded the feature set of the landline with caller ID, different ringtones based on the caller, speed dial and so forth. In the second half of the 1990s, however, manufacturers of these phones switched to 8051 compatible MCUs to reduce power consumption and prevent compact wall power adapters from overheating. Discontinuation, edit. On the 15th of April, 2024, Zilog announced the discontinuation of the Z80 processor, with orders being accepted until the 14th of June, 2024. The announcement included 13 variants of the Z80 processor, many of which being DIP40 variants of the chip. Zilog will continue to manufacture the upgraded Z80 version of the processor. See also, edit. 1S100 bus. 2SYMBOS. 3Z88DK. 4 microprocessor MPFI, Z80 training system. Footnotes, edit. 1 carat only INCMOS, national made known MOS version, according to oral history with Federico Fagin. 2 carat CMOS variants went up to 20 MHz and binary compatible derivatives went up to 50 MHz. 3 carat backwards compatible with Intel 8080. 4 carat Zilog included several traps in the layout of the chip to try to delay this copying. According to Fagin, an NEC engineer later told him it had cost them several months of work before they were able to get their PD780 to function. 5 carat. This was a fairly common feature of mini-computer designs of the era, and found its way into a number of early microprocessors. 6 carat Zilog manufactured the Z80 as well as most of their other products for many years until they sold their manufacturing plants and become the fabless company they are today. 7 carat. Although the 8080 had 16-bit addition and 16-bit increment and decrement instructions, it had no explicit 16-bit subtraction, and no overflow flag. The Z80 complemented this with the ADCHLR and SBCHLR instructions, which sets the new overflow flag accordingly. The 8080 compatible ADHLR does not. 8-carat notably to simultaneously handle the 32-bit mantises of two operands in the 40-bit floating point format used in the Sinclair home computers. They were also used in a similar fashion in some earlier but lesser-known Z80-based computers, such as the Swedish ABC80 and ABC800. 9-carat as this refresh does not need to transfer any data, just output sequential row addresses. It occupies less than 1.5 T states. The dedicated M1 signal, machine cycle 1, in the Z80 can be used to allow memory chips the same amount of access time for instruction fetches as for data access, i.e. almost 2 full T states out of the 4 T fetch cycle, as well as out of the 3 T data read cycle. The Z80 could use memory with the same range of access times as the 8080, or the 8086, at the same clock frequency. This long M1 signal, relative to the clock, also meant that the Z80 could employ about 4 or 5 times the internal frequency of a 6800, 6502 or similar using the same type of memory. 10-carat unlike the original NMOS version, which used dynamic latches and could not be stopped for more than a few thousand clock cycles. 11-carat the related 8086 family also inherited this register design. 12-carat this variable HL pointer was actually the only way to access memory, for data, in the data point 2200, and hence also in the Intel 8008. No direct addresses could be used to access data. 13-carat jump, JP, instructions, which load the program counter with a new instruction address, do not themselves access memory. Absolute and relative forms of the jump reflect this by omitting the round brackets from their operands. Register-based jump instructions such as JP, HL, include round brackets in an apparent deviation from this convention. 14-carat for example, on the 8080, a programmer might test the parity of a byte by adding 0 to it, by subtracting 0 from it, or by ORing or XORing it with 0. All of these are single instruction operations of the same speed and size, on both the 8080 and the Z80. If the programmer happened to choose to test parity by ORing or XORing with 0, then the Z80 will execute the program correctly. But if the programmer chose to test parity by adding or subtracting 0, then the Z80 will always reset the P/V flag to 0, since adding or subtracting 0 never causes an overflow or underflow, instead of assigning P to correctly indicate the parity of the byte, as the 8080 or 8085 would, and the program may fail. Nothing in the Intel programming manuals or other documentation for the 8080 discouraged use of arithmetic instructions, or prescribed using logical instructions, to test parity, so there is no reason that an 8080 programmer exercising recommended good programming practice should be expected to have chosen one of the ways that will work on the Z80 over one of the ways that will not work. 15-carat this common, but merely optional and not limiting, usage leads to the frequent but incorrect description of the Z80 in the Genesis as a sound processor. References, edit.
That was super long. It was super long. Now it's 2 p.m. and I need a break, and I am going to make a video on my language Danish about it. So I need a break charging my camcorder, and I can upload this. I can start upload this, but the camcorder's out of power. So I will take a break, and I'm going to make a Danish video. It's supposed to be in English, but I do in my language Danish for now.